Greetings to you. Welcome to physics class. In our previous class, we looked at simple AC circuits. We defined simple AC circuit as a path provided for the flow of AC. And then we also looked at the root mean square value of an AC, where we have I root mean square equals to I naught over root 2. We also looked at the circuit containing only a resistor, only a capacitor, and only an inductor. That a circuit that contains only a resistor, the current and the voltage, they vibrate, and then the same phase. And then the circuit that contains only the capacitor, the current and the voltage, they are out of phase, with the current leading and the voltage lagging. And then the circuit that contains only an inductor, they also vibrate out of phase, with the voltage leading and the current lagging. We also look at capacitive reactance and also inductive reactance. In today's video, we shall be concentrating on the circuit that AC series circuit that contains a resistor and a capacitor, and also a resistor and an inductor. So let's begin with this AC series, RC series AC circuit. So let's have our circuit diagram quickly. Let's draw something like this. This is our resistor with resistance R connected in series with a capacitor of capacitance C. And then this is our key. Our key down here, our ammeter to measure the AC. Then this is our AC source. AC source. And so here is the voltage. Let's demarcate this. This is the voltage across the resistor, and then the voltage across the capacitor C. Good. Now let's have our sinusoidal waveform here. Let's call this I, V, positive side of the waveform, 0, I, V. Now recall that in a circuit that contains only a resistor, the current and the voltage, they vibrate and they're in the same phase. So in that regard, we draw something like this. Let this be our voltage at time t in seconds. And let this be our current vibrating with the voltage in the same phase. Let's call this our time, our current. The current in the entire circuit. And then let's call this the voltage across the resistor R. And then, because in a circuit that contains only a capacitor, the current leads, we write again, we draw again, this down one, the voltage across the capacitor, its waveform will begin from here, come down here, come down here, and like this. And so we'll say this is the voltage across the capacitor C. When that happens, we have a Phasor diagram drawn this way. We call it Phasor diagram or vector diagram. So our Phasor diagram becomes something like this. The voltage across the resistor R and the current will be in one direction. And so we extend our line down here. Then we call this voltage across the capacitor and then the capacitive reactance. Then here is 0 down here. Here is the effective voltage and then the effective resistance offered by the resistor and the capacitor called the impedance in this direction. Then if you join this line, you will discover that up here we have our V, R, R. And down here is also your V, R, R. And then this side is your VC, XL, where XL is the XC is the capacitive reactance. And so here becomes our first angle. Then because the current leads, we draw something like this. Current leads with this angle. Then let's start writing. From this diagram you see on the board, from your SOHCAHTOA and also Pythagoras theory, we write the effective voltage, which is this R in the circuit, is V squared from Pythagoras theory equals to V squared plus V R squared plus V C squared. So your V is equals to the root of V R squared plus V C squared. Let's call this our equation number 1. That is that. And then the effective resistance in the circuit, known as the impedance, is given as Z squared is equals to what? Your R squared plus XC squared. Then your Z is equals to the root of R squared plus XC squared. Let's call this equation number 2. Equation number 2. And so we write again. So the currents in the entire circuit, the angle with which the current leads is giving us tan phi, which is equal to opposite. Tan phi is giving us what? Opposite over adjacent, meaning V voltage across the capacitor divided by voltage across the resistor, which is the same thing as the capacitive reactance C divided by R. You can call this your equation number 3. Then the next thing is the entire current in the circuit. Recall from Ohm's law, V is equals to IR. So our R is behaving like Z. Our R will be replaced by Z. So we write that V is equals to IZ. We call it equation number 4, where Z is the impedance and I is the current. Then for your root mean square value, you know that your V naught is equals to your I naught Z. You also know again that your, okay, let me bring this up quickly. This is equation number 4. You also know, let me clean this quickly. You also know that V root mean square is equals to I root mean squared, which is, times Z. You can call this your question number 5. Also, your V naught is equals to your I naught Z. You can call this your equation number 6. Now, still from here, voltage across the capacitor is the same thing as the entire current in the circuit, and then the capacitive reactance. You can call this your equation number 7. Then voltage across the resistor is the same thing as the current. It's the same current will flow through them. Then you have I naught, then you have R. You call it your question number 8. I believe these are the equations you have here so far. So let's look at what happens when you connect a series AC circuit with, you connect R and L in series in an AC circuit. We'll quickly clean this one. So we have RL series circuit. So this is our inductance. Inductor with inductance L. Inductance with inductance L. Voltage across the inductor. So let's draw our Phasor diagram, our sinusoidal waveform again. Something like this. Your I, V, positive, I, V, negative 0. Now, still what we said earlier, we'll still repeat it again. The resistor in this circuit will make the current, the entire current, and then the voltage across this to vibrate and be in the same phase with this waveform. Against time, seconds. Again, we use the red. We use the red for our current. The current and the resistor will be in phase. So this is the current, and then this is the voltage across the resistor R. So, since we said that in a circuit that contains an inductor, the voltage across the inductor leads. The inductor causes the voltage in the circuit to lead and the current to lag. So we begin from here. That our inductor, its waveform will begin from here. Come down here. Go this way. Come down here. Like this. As you can see, in each, this is it, this is it, this is it, this is it. So the voltage, so we call this the voltage across the inductor L. When that happens, we have a phasor diagram this way. Phasor diagram or vector diagram is given as this. So this is the voltage across the resistor, the R, and then the current to be in the same direction since they are in step or in phase. Then up here will be voltage across the inductor and the inductive reactance L. Then if you draw a straight line here with an arrow, the voltage is leading with an arrow. Then with an angle phi, which is the phase difference. And so from your Pythagoras theory, here is your V R, R. Up here is also your V R, R. Then this way is also your VL, XL. Now we write again. Down here is effective voltage and also the effective resistance in the circuit offered by the resistor and then the inductor called the impedance. So from Pythagoras theory, you know that the hypotenuse V squared is equals to VR squared plus VL squared. VL squared. How do we call this? Let's call this our equation number what? I've forgotten. Let's leave it that way. And then we write again V is equals to the roots of VR squared plus VL squared. Name it the way you want it to be. You can pause the video and record the equations. And then also your effective resistance in the circuit impedance Z squared is equals to what? It's equals to R squared plus XL squared. And then your Z is equals to the root of R squared plus XL squared. Name it XL squared. And so the angle with which the voltage leads is given as tan phi, which is equals to opposites over adjacent. Opposite over adjacent, that is V, voltage across the inductor divided by voltage across the resistor, which is the same thing as the inductive reactance L divided by the resistor. Name it. And then the entire current in the whole circuit is given from Ohm's law. V is equals to IR. We write that V is equals to IZ, because Z is the effective resistance in the circuit. So you can also name that equation. So we write again that from the root mean square value, you know that your V naught is equals to your I naught, your R. And then you write again, this is congruent to V naught is equals to I naught Z. Name that equation as well. You also know that your V root mean square is the same thing as I root mean square. This is congruent to V root mean square, which is equal to what? I root mean square Z. Name it. And so the voltage across the voltage, that is VR, from Ohm's law, we can write that our VR is equal to I R. Name it. Also, the voltage across the inductor L is given as I times XL. Name it. So these are all the possible equations I think you can encounter in this topic. So when next we meet, we shall be using all these equations with the ones in the first video to do a whole lot of calculations, and then in our upper next video we shall be looking at a circuit containing a resistor, a capacitor, and an inductor all connected in series. I hope you enjoyed this class. Stay safe and stay blessed. God bless you. Thank you.